Good morning to everyone. Today we have to see ultrasonic testing. Myself, Manihindan S from Erode Second Engineering College in the Department of Mechanical Engineering. Today we have to discuss detailedly about ultrasonic testing. Ultrasonic testing is one of the important testing process which is carried out in non-destructive testing methods. Non-destructive testing method is one of the important testing method which is carried out in mechanical area to investigate the properties or the defects which are present inside the material. For example, you have to find out the flaws or air cracks with the help of some of the equipments which are named as ultrasonic testing. In this ultrasonic testing, we are using sound waves to propagate into the workpiece, and we get a signal. With the help of that signal, we have to see the defect, which is exactly where it is located. So now we have entered into the topic. What is meant by ultrasonic testing, which is applicable and most suitable for metallic as well as non-metallic materials. In ultrasonic testings, high frequency sound waves should be propagated into the material. For example, the frequency from 1 to 10 megahertz is typically used in ultrasonic testing methods, in which we have to conduct an examination and we have to take the measurement where the exact flaw is located, right? And in ultrasonic examination, we have to conduct it on a wide variety of material forms, including casting, forging, welds, and composites. By this method, the surface and internal discontinuities. For example, in liquid penetrant testing, we have to examine the surface discontinuities alone. But in ultrasonic testing, we have to examine the internal discontinuities, such as lapses, seams, voids, cracks, blowholes, inclusions, and lack of points can be exactly and accurately evaluated in this type of ultrasonic testing methods. Most importantly, which is most suitable for metallic or non-metallic materials. So the internal discontinuities, such as we already noted that lapse seams are internally found, but it will not be examined with the help of our naked eye. So we have to propagate the sound waves into the material. With the help of the frequency of that sound waves, we have to exactly identify where the defect and how it is propagated into the material. I'm telling about the length and breadth of the defect. So we have to find out the material defects. This is the basic principle of ultrasonic testing setup. In this, the left side indicates the workpiece sample. At the top of the workpiece, we have to fix the probe. We have to move the probe along the workpiece with a measured length. Before we have to examine the workpiece, we have to uh, decide where we have to fix the props and we have to measure. Equal importance should be given to equal length. So the sound reflected back to the probe is displayed on the flaw detector, which is shown here, right? First, initial sound waves are propagated as front wall echo, and finally, the sound waves propagated along the workpiece and returned back to the actual transmitter. In this type of props, the probe is acting as a transmitter as well as a receiver. Transmitter transmits the signal as well as the sound propagates from front wall to the back wall, and once the sound waves reaches the back wall, it repeats, return backs to the receiving end. So with the help of the transmitting and receiving end, we get a signal which is displayed in the monitor. If there is no defect is found inside the material, there should be no uh, flaws or no defects inside the material means there is no sound wave propagation curve along the displays. We only get the front wall and the back wall echo signals only. The basic principles behind that is first the distance the sound traveled can be displayed on the flaw detector. The screen can be calibrated to give an accuracy reading of the distance. Signals from the back echo. It shows that the arrow mark indicates the first arrow words indicates the front wall, whereas the second arrowhead indicates the back wall echo signal. If we found any flaws inside the material means in between the front wall and the back wall echo, we find a one of the curve we find out. With the measurement of that curve, we have to find out how much dimension of flaw is found inside the material. We have to find out. Here, a defect is finded inside the material means we get a defect signal, right? It shows that the peak of the signal it shows where the exact defect is. Initially from front wall, and the second curve indicates defect signal, and third signal indicates that back wall echo. In previous picture, we seen that the back wall echo's peak is much more when compared to this picture because that the sound waves propagated into the defect, it targeted on the defect. Automatically, the frequency of the sound waves will getting decreased. So due to that, the signal's wavelength getting decreased, and it again hits back to the back wall echo with a low frequency. It shows that the peak of that amplitude signal is very less. It shows we have to find out the main important factor behind ultrasonic testing is that we find out any defect inside the workpiece means we have to find out exactly where it is. In liquid penetrant testing, we have to apply the penetrant and developer along the surface of the workpiece, and finally we have to find out where the flaw is, right? We have to simply find out is the workpiece is defected or not. That's it. But in ultrasonic testing, the flaw is actually finded out inside of the material. So we have to deeply monitor how much the defect will penetrated in the material. So in further application, we have to use it or not. So for the final decision, we have to take the exact measurement of the defect. It shows the depth of the defect can read with reference to the marker of the screen. It shows that, right? How much distance from initial position to reach the defect. Exact measurement should be shown. So we have to detailedly study what is the theory behind the ultrasonic testing. In this testing process, the ultrasound transducers connected to the diagnostic machine is passed over the object being inspected. I already told that there are different types of probes are there. One of the probe having both categories. The single probe it transmits and as well as receives. Uh, one more type of probe is there in which one end is connected with the transmitter and another end of the part is connected with the receiver. So in this type of transducers is typically separated from the test object by a couplet. Basically, the matting surface of the workpiece and the transducer should be coupled with couplet because uh, the sound waves propagate some noise or some vibrations, right? That vibrations will not interfere the workpiece. So we must um, go for a couplet. It's basically an oil or by a solvent of water as in immersion testings. However, the ultrasonic testing is conducted with the electromagnetic acoustic transducers in which the couplet is not required actually. Electromagnetic acoustic transducers will not require couplets because electromagnetic transducers are magnetized. So there is less possibility of damaging to the workpiece. So couplet is not essential. ultrasonic waves, reflection, and the attenuations. We have to see it in further. In this picture, we clearly noticed that how much uh, the defect is involved in the workpiece, right? And the bottom of the surface, we are noticing that the probe, this is one of the transducer, this is the workpiece. From the starting edge to the ending edge, we are slightly moving the probe from starting edge to the ending edge. We don't know where the exact defect is located, no. So we have to find out the defect from starting position. Initially, the transducer is set here, and we have to set the signal. It transmits and return backs. So here there is no defect means, as usual, we get a simple front wall echo and back wall echo alone. Then after, we have to move the transducer to the next part of the workpiece. Then we have to transmit the signal. Here, we have to transmit the signal from here to here. Once the crack is find it out, we get a crack echo here, right? The crack is of minimum or in a small dimension, we get a peak like this, right? Once exactly the sound is propagated through the crack means it will not transposed through the crack. So immediately it will return back to the receiver. So the peak signal should be shown as like this, right? How sounds work. So we go for sound means the basic dependence we are need is wavelength, frequency, and velocity. The common theorem behind wavelength is the distance required to complete a single cycle is known as wavelength, and it is commonly measured in meter or in mm. Whereas frequency is a number of cycle per unit time. That is frequency, right? It is commonly we are noticing in hertz or cycle per seconds. Whereas velocity is how the sound waves are propagated. Actually, it is a distance per unit time. That is velocity, right? It is commonly noticed in meters or meters per second, right? Meters per second is the velocity, right? It is a common example. Sound is produced by vibrating a body and it travel in a form of a wave. Commonly, in engineering physics, we know that with the tuning fork, we have to create a noise, and with the help of that tuning effort, we get a signals, right? It is the best example for an ultrasonic testing. Similarly, we have to uh, create a sound waves with the help of a transducers, with the in which the sound waves travels through material by vibrating the particle that make up the material, right? It's a cube which is a form of number of small cubes, each cubes having atoms. Once you disturb a single phase of atom, it automatically transforms its vibration throughout the cube. Depends upon the force we are acting on the cube, right? The pitch of the sound is determined by frequency of the waves. The pitch is nothing but the sound is determined by the frequency of the waves. Vibrations or cycles completed in a certain period of time, right? Ultrasounds is a sound with a pitch too high to be detected by the human ear. Properties of sound waves. Sound cannot travel in vacuum. Actually, uh, if a crack is found inside the material means the sound will not propagate through the crack, right? Considered as the crack as a backward. So immediately it hits the crack and return backs to the receiver. Sound waves travels from transducer to the crack, and immediately if they found any crack inside the material, it detected and return backs to the uh, receiving end immediately. So sound waves cannot travel in a vacuum, as well as sound energy to be transmitted or transferred from one particle to another, as we seen in the before picture, right? Once we disturb a single atom, it automatically transfers its vibrating signal to another atom, another atom, another atom. Sound waves. All sound waves, whether audible or ultrasonic, um, or mechanical vibrations involving movement of medium in which they are traveling. Audible range is as human ear are able to hear, whereas that is audible range. All sound waves, whether audible or ultrasonic, audible range is recommended for human eyes, whereas more than 10 frequency or 20 frequency we are getting means it will automatically damages our ear. So whenever we are taking care of the process, we definitely take care of our human ear. The sound waves may be transmitted through any material which behaves in an elastic manner. In this, we are categorized into three different types of waves: longitudinal waves, transverse, and rally waves. Whereas transverse are also known as shear waves, in which surface are also known as rally waves. Ultrasonic waves and ultrasonic waves are very similar to light waves in that they can be reflected, refracted, and focused. It is similar to the light waves in which it can reflect, refract, and focused. Reflection and refraction occurs when sound waves interact with interface of different acoustic properties actually. Reflection and refraction occurs when sound waves interact with interface of different acoustic properties. In solid materials, the vibration energy can be split into different wave modes. And the wave encounters an interface at an angle over the 90 degree actually. Right? In this picture, we clearly noticed that when the wave encounters an interface at an angle over a 90 degree, right? In which the ultrasonic reflection from the presence of discontinuities or geometrical features enable detection and location. It will be shown with the help of the displays. The velocity of sound in a given material is constant and can only be altered by the change of mode of energy. We have to see one by one. First, we have to see the longitudinal waves. Longitudinal waves are waves in which displacement of medium is the same direction as or the opposite direction to the direction of the propagation of the wave. Mechanical longitudinal waves are also called the compressional waves because they produce compressional or rarefaction when traveling through a medium, and the pressure waves because they produce increase and decrease in pressure. Commonly, the longitudinal waves are in this picture we are see clearly the longitudinal waves are waves which uh, displacement of medium is the same direction or opposite direction to the direction of propagation, right? In this we have to see the compression and the rarefaction waves. The wavelength displacement indicates where the longitudinal wave is compression or rarefaction. The distance between the wavelength is differs. It is known as rarefaction, whereas it is closely indicated means it's a compressional waves. Transverse or shear waves. The transverse waves is a moving wave that consists of oscillations occurring perpendicular to the direction of energy transfers or the propagation of the wave. In these transverse waves, these are commonly transverse waves. It's an example of a seawater traveling path. The in a transverse waves is moving in the positive x direction. Its oscillation or in up and down directions. That is y and z directions. We are seeing the transverse waves. Light is an example of transverse waves, while sound is a longitudinal wave. A ripple in a pond and a wave on a string are easily visualized as transverse wave. They set a ripple in a pond. When you drop a stone in a pond, it creates transverse wave. That is, they said it's a good example. Here we have to see the transverse wave. Transverse waves have an amplitude, um, wavelength, crest, and peaks. We already know that what is meant by one cycle, one complete cycle. What is the distance traveled, and in this They created a displacement versus distance, and the third one is Rayleigh waves. This type of waves can travel only along surface bounded on one side by strong elastic force of sides and on other by nearly non-existent elastic forces between gas molecules. Commonly, surface waves are essentially non-existent in the solid immersed in liquid, unless the liquid covers the solid surface only as a thin layer surface. These are the layery surfaces. The particles which vibrates or looks like an elliptical orbit, right? This is the one of the best example for a Rayleigh waves. It's a simple form. So there are many different mode of wave propagations. In this table, we have distributed the wave type versus the particle vibration. In longitudinal, it is also known as compressions, in which parallel to the surface. That means the particle vibration is parallel to the wave direction, whereas in transverse, perpendicular to the wave direction. Whereas in Rayleigh waves, elliptical orbit, symmetrical mode, and the last one is lamp waves. Lamp waves are components perpendicular to the surfaces. There are different types of sound wave propagations. This is one of the velocity. The velocity of a sound in a particular material is constant actually. It is a product of density and elasticity of the material. It will not change if frequency changes. Only the wavelength changes. Okay, these are the basic phenomena of velocity. Examples of velocity for steel, water, and air, which are noticed here. The exact picture of the velocity, how it travels, or clearly noticed below. For steel, it is 95960 meters per second. For water is 1470 meters per second. For as air is 330 meters per second. Right. Okay, we have to find out the velocity for longitudinal waves. The sound speed of the sound in a solid material can be found with the given formula. We have to find out. For the Rayleigh waves, we have to find out the speed of the sound with the help of the given formula. These are some of the velocity values for the given materials. The longitudinal waves travels faster than shear waves commonly. Longitudinal waves are approximately twice as fast as shear waves actually, right? In this below table, we noticed clearly the compressional velocity as well as the shear velocities for the aluminum, steel, cast iron, copper, and titanium meters per second values. This is acoustic spectrum, whereas audible and ultrasonic, how it differs, right? Below 20 kilohertz is considered as audible range, whereas greater than 20 kilohertz is considered as ultrasonic sound up to maximum frequencies, right? This picture clearly indicates what is audible or sonic, whereas ultrasonic will starts from 10 kilohertz. And this it's a frequency. We all know that. So one cycle per round, 3 cycle per round second, and 18 cycle per round second. Frequency. Generally, the choice of test frequency depends upon two factors: the minimum size of the defect, which is to be detected, and the medium in which such a defect is shooted. Right? It's a wavelength. Wavelength is a distance required to complete a cycle, which is a wavelength. Sound waves are the vibrations of particles in solids, liquids, or gases, whereas particles vibrates about a mean position. This is the comparison between the wavelength and the frequency. The higher the frequency, the smaller the wavelength. It's a well-known thing. The smaller the wavelength, the higher the sensitivity. Sensitivity is the smallest detectable flaw by the system or a technique. Every system has sensitivity, right? It's the smallest detectable flaw. by the system or a technique. Right? Reflection. Light can bend and move through the material, which is called refraction, or light can bounce off the material, which is called reflection, which is called reflection. When sound waves in a given medium, it strikes the surface of another medium and bounce back in some other direction. This phenomenon is called reflection, in which the sounds are called incident and reflected sound waves. Commonly, the light can travel along the um, bends also, which is named as a reflection, right? This divergence, the term used to describe the spreading of ultrasonic waves behind the near field, the function of transducer diameters and the wavelength in the medium. Divergent angle, we have to see the divergent angle within the far field between the beam axis and the beam edge at which the amplitude has fallen by the defined level. And next thing is scattering and absorption. Scattering, it is the defect, it is the reflection of sound beams from its original direction of propagation, whereas absorption is a conversion of sound energy from one form to some other forms. It's an attenuation in sound waves. It is a combined effect of scattering and absorption. We already seen what is scattering and absorption. It's a combined effect of scattering and absorption. It states that when a sound beam travels through any medium, its intensity gradually reduces due to scattering and absorption. Right? The common term is noted below. Uh, the various types involved in ultrasonic testing are noticed here. Ultrasonic testing is widely used to know in NDT. The common three categories are pulse echo and through transmission, normal beam and angle beam, contact and immersion type. These are the three different categories in which pulse echo and through transmission is first category, and second one is normal beam and angle beam, and third one is contact and immersion type. Right? First, we have to see the pulse echo method. In this pulse echo method,